Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be looking at a question that came in my lower seed catch-up exam for the first sequence. So I can say majority of the students complain about question 3b, proving that if a is equal to the GCD of two integers and b is the LCM of the two integers, then the product of the GCD and the LCM is equal to the product of the two integers. So that's what we are going to be doing in this video. Alright, so let's get started. So this is what we are proving. We are proving that if a is the GCD of two integers and b is their LCM, then the product of the two integers is the product of their GCD and their LCM. Alright, so basically let's try to take some basic cases. Okay, now we know that the LCM, for example, the LCM of 2 and 4, that's the least common multiple, is 4, right? And the GCD of 2 and 4 is 2. So therefore means that if we take the LCM of 2 and 4, right, and you multiply it with the GCD of 2 and 4, you're actually supposed to have 2 times 4, which is 8. Okay, in fact you see that the LCM is 4 and the GCD is 2. You see that when you multiply both of them, you're going to have the product of the two integers themselves. Okay, so that's basically what we have here. But now we have to prove this. So we are going to use the fact that every integer can be expressed as a product of its prime factors. We call that statement a fundamental theorem of arithmetic. So the fundamental theorem of arithmetic states that every integer can be expressed as a product of its prime factors. So that's what the theorem says. So we are just going to consider a general, in fact we are going to look for the prime factorization. So expressing integers as a product of their prime factors is simply what we call prime factorization. Okay, so for example, if I say give me the prime factorization of let me say of any integer, let's say, okay, give me the prime factorization of 20. All you need to do is you have to express 20 as a product of its prime factors. The prime factors of 20 are just 2 and 5. So you have 2 times 2, which is 4, then times 5. Okay, so if you want to simplify, we can say, okay, this is simply 2 squared times 5. So this is a prime factorization of 20. What about, let's say, okay, let's find the prime factorization of 45. I'll first of all break it down into 9 times 5. Okay, now since 9 is not a prime number, I'll bring 9 into what? 3 squared. That's 3 times 3, right? Since 3 is a prime number. So this is basically the prime factorization of 45. So the fundamental theorem of arithmetic states that every integer can be expressed as a product of its prime factors in exactly one way, actually, to complete the statement, in exactly one way. Okay, so basically every integer, let's say n, can be expressed as a product of its prime factors. So let's say the prime factors of n, you have p1 raised to the power maybe n1, okay, times p2 raised to the power n2. Remember that our n1 here just represents the number of times the prime factor p1 appears in the prime factorization of n. You see, here was actually 2 times 2. Okay, so since 2 appears 2 times in the prime factorization of 20, then we're just going to write it as 2 squared. So to always get the LCM or the GCD, we first of all find the prime factorization, then we use the formula. Okay, so let's just assume that this number n has n prime factors, okay, because it's an arbitrary integer that we have taken, so we cannot get the number of prime factors without knowing exactly its value. So Pn right up till Nn. Alright, and then let's say, okay, remember that this P1, P2 right up to Pn simply represent the prime factors of the number n, and then small n1, small n2, small right up till small nn represents the number of times these prime factors appear in the prime factorization of n respectively. Okay, so let's say, okay, the integer m is equal to, you also need to have the same prime factors p1 raised to the power the number of times it appears times p2 raised to the power the number of times it appears right up till the last prime factor of the integer m raised to the power the number of times it appears in the prime factorization. Okay, so if we're able to do this, okay, then we can deduce or conclude that the LCM of n and m is just equal to, so what I do is that I just make sure that this P1 should be in n and in m, P2 should be in n and in m, and so on and so forth. So you have P1 to the power, to get the LCM we take the maximum of n1 and m1. That's what we do. Maximum of two numbers means you take the one that is bigger. P2 raised to the power the maximum of n2 and m2, and finally we move right down till Pn raised to the power the maximum of nn and mn. Okay, and what about the greatest common divisor, the GCD? The GCD of n and m is equal to, instead of having maximum here, you just replace the maximum with minimum. So rather, instead of maximum we have minimum, instead of maximum we have minimum, instead of maximum we have minimum. So basically these are the respective definitions of the LCM and the GCD once we have the prime factorization of the two integers. Alright, so for example, if I ask you to find the LCM of 20 and 45 and the GCD of 20 and 45, now you clearly see that we have found the prime factorization of 20 already, okay, and then we have found the prime factorization of 45 already. But if you verify, you see that if you call your P1 to be 2, there is no P1 here. So what you simply do is that you attach a 2 to the power 0, okay, so that your P1 should be there. If you call your P2 to be 3, there is no P2 here, so we attach a 3 to the power 0, so you should have a P2. And you see that your P3 is just 5 since 5 is common. Alright, so if I say, okay, give me the LCM of 20 and 45, all you do is that you take the first prime common factor, which is 2, raised to the power. Since it's LCM, we need to take the maximum of the powers of 2 in the prime factorization of the two numbers. The power here is 2 and the power here is 0. The maximum of 2 and 0 is 2 because 2 is bigger, okay. You multiply with the next prime factor, which is 3, raised to the power the maximum of 0 and 2, which is 2. And finally you multiply with 5 raised to the power the maximum, you just see 1 and 1, okay. So there's no maximum between 1 and 1, so it's just 1, okay. So you just multiply everything. Here is 4 times 9 is 36, and 36 times 5, you're going to get the response. Let me say 9, 45 times 4, 45 times 4. In fact, guys, you just find it there, I don't know. Okay, now what about the GCD of 20 and 45? Okay, so we take the very thing but now we are taking by the minimum. The minimum of 2 and 0 is simply 0, okay, times, now you have 3 raised to the power, the minimum of 0 and 2 is 0 as well, and you multiply with 5 raised to the power 1 because the minimum of 1 and 1. So here we have 1, okay, here we have 1 times 1 is 1, and here we have 5, so the result is 5. So the greatest common divisor, or the highest common factor of 20 and 45 is 5. So basically that's how we use the notion of prime factorization and the formula to get the greatest common divisor and the least common multiple of two integers. Okay, so let's get back to what we have to do. We have to prove that if, okay, in fact, let us look at examples here. Now you verify that if you actually multiply the LCM, okay, and the GCD, you should get back the product of the two numbers. 20 times 45 is 900 because it's 450 times 2. Now if you multiply all of this with 5, you should get 900. So you can take 5 times 5, 25. Okay, 25 times 9, then times 4, or 25 times 36. I think it should give you 900 there. Okay, all right, so let us now prove that if A is the GCD of N and M and B is the LCM, then AB is equal to NM. So that's what we have to prove. So we are going to build our proof based on these definitions of the least common multiple and the greatest common divisor of two integers. So let's just multiply. Okay, so the LCM of N and M multiplied by the GCD of N and M is equal to, it just means, what do? I multiply this, okay, and then, so this is the LCM, let me just keep it separately, and then you multiply it with the GCD. Here is a GCD, okay, then we are going to bring like terms together. Alright, so let me just decrease the size so that it enters. Alright, so this is what we have. The LCM times the GCD is equal to this. Now we are going to apply indices. Okay, we are going to apply indices. So what are we going to do? We are going to say this is equal to, now I'm going to take P1 to the maximum of that, and then I'm going to pair it with P1 to the minimum. Okay, I'm going to pair it with this one because they are like, they have the same base, and we know that if you are multiplying two things that have the same base, you simply add their powers. So I just need to erase this and add it to the other power here. So I just have plus the minimum, okay, then times, you now take P2, okay, and you multiply it with this other one. You just have to add the power to this other power here. So you have plus this. So you multiply till we arrive at Pn to this maximum. Okay, we just need to add this other part to it. Alright, now what do we do next after having this? Now you have to note that if you take the maximum of two numbers and add it to the minimum of the very two numbers, the result is just the sum of the two numbers. Now in this case, we don't actually know if n1 is greater than m1 or n1 is less than m1. But if we assume that n1 is greater than m1, okay, what does this mean? This means that the maximum of n1 and m1 is the bigger one, which is what? n1. It therefore means the minimum will be m1. And you see that if you take the maximum plus the minimum, it's just going to be what? n1 plus m1. Okay, now so let me just say, so the minimum of n1 and m1 is equal to m1. Okay, so in conclusion, we are saying that if you take the maximum of the two plus the minimum of the two, you simply get the sum of the two numbers. So if you take the maximum of the two plus the minimum, you simply get m1 plus n1. That's what you have. Okay, so with that said, you also see that if you actually consider the contrary, if you actually say, okay, if m1 is bigger, it means that the maximum will be m1 and the minimum will be n1, and when you see add, you're going to have m1 plus n1. But we know addition is commutative, so m1 plus n1 is the same as n1 plus m1. So in either case we have same result. So this will just be equal to p1 raised to the power n1 plus m1 times p2 raised to the power n2 plus m2, right down till pn raised to the power nn plus mn. Okay, so what does this give us at the end of the day? So I'm going to write it as p1 raised to the power n1 times p1 raised to the power m1. Okay, then continue the next term. So let me call this one the first term. The next term will simply be p2 raised to the power n2 times p2 raised to the power m2. We multiply till we arrive at pn. So we arrive at pn raised to the power nn times pn raised to the power mn. Okay, so this is equal to, and I'll have p1 raised to the power n1 times p2 raised to the power n2, right down till pn raised to the power nn. So here is it. So I have this first portion, so I have this, then I multiply it with, and I have p1 to the power m1 times p2 to the power m2, right down to pn to the power mn. Okay, so I have this other part. So you clearly see that those two quantities represent m and n. So this is equal to n times m. So we can conclude that the LCM of n and m multiplied by the GCD of n and m is equal to nm as required. Okay, so those of you science students, especially science 4, I think I remember I did this proof with you guys during prime factorization, though I never did in the other classes, but I think I did this proof with you guys, so you should not be complaining that exam was hard. It's basically just for you to reproduce what I gave you. So in the other videos, I'm going to do the other questions that you said you had difficulties in, but let me just analyze all the questions together. Okay, now the question 3a was to prove that 3 divides m cubed minus m for all integer values of m, and I said you can use any method of your choice. So some people were saying that they use counter example. I'm going to mark it wrong. Why? Because counter example is used to prove that a statement is false. Okay, so you cannot use that here. So we have to prove that 3 divides m cubed minus m. You could use induction. Yes, induction is the best to do this. So you have to prove that m cubed minus m is a multiple of 3. So review your lesson on divisibility. What about finding the prime factorization of these two numbers? I just explained prime factorization, expressing the ratio of the two numbers in the lowest form and finding the LCM and GCD. Find the number of positive divisors. Review your notes. I believe that's all. Yes, that's all for. I believe all of you guys solved this first question correctly. Now let's get to the MCQs. Alright, so here we were just supposed to multiply both sides by the multiplicative inverse of 20 in mode 97, which is 34, and it is your solution. You're going to get option A as your answer. Here, how many 2-digit numbers with non-zero first digit exist such that the sum of the digit is 6? We are going to look at that. We are going to look at this question in class, in our next class. Here you just have to verify that the GCD of 2 and 1 divides 4. Clearly the GCD is 1 and it divides 4, so there are solutions. You do your backward substitution and you do your initial solutions. I think you're going to get option A as your response. Okay, now what is the remainder when 5 to the power 20 is divided by 10? Result is 5. Remember that I said the remainder when a certain number is divided by 10 is simply the unit digit of that number. Now 5 to any power will end with 5, so no matter the power, 5 to that power will always end with 5, and it is equivalent to saying that 5 to this power divided by 10, the remainder is what we call the unit digit, which is 5. And here, which of the following statements is true? I tried to bring in a relationship. I tried to bring in a Wilson's theorem here, though I gave option A. In fact, option A is wrong. Yes, option A is wrong. Option B, most of you take option B, you fail. So option B is very wrong. Let me put it in red. Why is it wrong? Now the Fermat's-Little theorem says that if A is any integer and P is a prime number, then A to the power P is congruent to 1 mod P, provided your integer A is not divisible by P. So the statement is incomplete. So if you take B, you're failed. So the answer is basically none of the above, because we know that for a linear Diophantine equation to have integer solutions, the GCD of A and B must divide C, not that must divide C minus A. So question 5, option D is correct. So basically that was the exam. See you guys in the next class and see you guys in the next video as well. Thank you for watching. Subscribe to the channel, turn on your notifications most importantly, so that when I upload the other videos you'll be notified to come and watch. Share with your friends. If you're joining the channel for your first time from a different school, don't bother. The organization